I want to now illustrate for you how to solve a pretty important problem type. Namely, it's typically referred to as the Atwood system. Two masses around a pulley. So we have mass M1 and we have mass M2. So they're connected across a pulley that we're going to assume is frictionless right now. We got the weight of each. Weight 1 is M1G. And then weight number 2 is M2G. Now you could probably guess that if these were exactly the same masses, that they would just sit there and not accelerate, and you'd be correct. What we're going to do, though, is consider the tension in each string, in each side here, while the condition exists that one is bigger than the other. Namely, M2 is bigger than M1. So we actually have an acceleration upward here, downward here. Since they're connected by the string, the values of those accelerations must be the same. So M2 is bigger than M1. Let's find the acceleration, the tension in string 1, the tension in string 2. Now, mass M1, a half a kilogram, where M2 is a little bit more, 0.51 kilograms. Now, this is another system that we can demonstrate, and I will show you how this looks. But let's go through the analysis here in any case. So to get the acceleration, we have F net over M total. So the sum of the forces over the mass. That basic equation, the net force is important, because really we have a reversal of direction from the pulley. But these two things are opposing each other, aren't they? Yes. Weight acts straight down. Those forces are down, but because of this string connecting them, they're really fighting each other. They're not going in the same direction as far as this system is concerned. So it's weight 2 minus weight 1 over M total, which is M1 plus M2. That's what we're going to analyze. So it's M2G minus M1G over M1 plus M2. And I'm going to factor out the G. All right, just to simplify it a little bit. Now, let's plug in numbers. 9.8 meters per second squared, the acceleration of gravity, times the difference in the masses, divided by the addition of the masses, gives us 0.097 meters per second squared. A very small acceleration. And hopefully, if we hook this up to a computer and actually let it run, we should be able to validate that indeed the acceleration is that very small amount. If you think about it, the net force is really tiny because these two are opposing each other. The net force is this very small number over here, and you're dividing it by the entire mass, because the entire mass is being accelerated by the difference between this force and this force, not the addition. If you think about it, the acceleration was pretty easy to solve. Now our next task is to determine the tension. Well, here it sits. We got M1, M2, gravity acting on it. So you might wonder to yourself, is it the weight of mass 1 or the weight of mass 2? And we just learned that tension is the same everywhere, right? We're also assuming, if you're thinking critically about this, that this pulley is massless. So if it rotates, it doesn't matter, doesn't affect the tension. That may not have made perfect sense to you, but trust me, that's important. If this is massless, there's no friction here to roll it, then it doesn't change the tension in either string. So we're assuming the tension is the same, aren't we? But we got different masses hooked to the two sides. Well, I can demonstrate with a scale, ask me to do that, that it's more, it should be more than M1G. It's kind of like an elevator. When you accelerate upward, do you feel heavier or feel lighter? You'd say to yourself, well, I guess I feel heavier while it's accelerating up. And if you're accelerating down the elevator, for a brief moment at least, you feel lighter. So we would guess then it'd be less than M2G. Well, that may be starting to make some sense to you to resolve this little dilemma. M1G, by the way, is 4.9 newtons. M2G is 5.00 newtons. All right. So let's look at tension 1. Let's analyze it. So we're going to analyze this side, this object, in a free body force diagram. Here's where a free body force diagram really is helpful. We're going to look at all the forces acting on M1. So let's do it. We have weight, M1G. We have tension acting up, T1. As far as I can tell, there's no other forces acting on it. Acceleration is upward. So that's really important because now we know which force wins, and it's not the weight. Rather, it's the tension to provide an acceleration upward. So F net equals M1A for this object. Just by definition, the net force is its mass times acceleration. We need to start the equation in the direction of acceleration because it points to the larger force, which is T1. So T1, so here we're going to start our equation. Can you follow the path? So we have T1, the bigger force, minus the smaller force, and that is F net. And that's equal to M1A. So T1 equals M1A plus M1G, which is M1A plus G. Now we can plug in the data. Half a kilogram, acceleration 0.097, G is 9.8, and it gives us a tension of 4.95 newtons. Bingo! Not a big problem, and it was a good example of how to solve a tension problem using a free body force diagram. Now let's do it to the other side as well. Okay, so let us do the tension on the other side, T2.
Oh.
Yep, that's right. Okay, free body force diagram. On M2, we have the weight of M2 acting down and tension acting upward. So there it is. Now the acceleration is down. We know which direction is the bigger force. It's in the direction of the acceleration. Isolating M2, the force of gravity pulling down is greater than the tension acting up, which is the only way to get this mass to accelerate downward. So F net, M2A, and start the equation with the bigger force. We know that the net force then is the weight minus the tension. So that's M2A. So solving for T2, M2G minus M2A, which is M2 times G minus A. You might notice that this differs in the other with just this sign. So let's go ahead and plug data in. 0.51 times 9.8 minus 0.097 equals 4.95 newtons, which is exactly what we had for the tension T1. And this graphic is just showing a little visual of the tension at any given point that there's little action-reaction pairs there. But the important thing here, we demonstrated that the tensions are the same. Now if we just held M1, kept it from accelerating, then the T2 would be the weight of mass 2. If we held M2, kept it from accelerating, the tension in the whole thing would be the weight of M1. But that's not the scenario we have. We let it go, the whole thing accelerates, and it increases the tension here, decreases the tension here. Turns out those effects are equal, the increase and the decrease, so it ends up being halfway between the two. That would be different if there was friction to turn this pulley, but there's not, so let's not complexify it here anymore. But now you know how to analyze two masses over a pulley, an Atwood system, and use these principles to solve similar problems as well. And that'll conclude our little introduction to Newton's laws.